Let's see one example. So in this example, we're given the 100 Newton force and the slope triangle, where we have the triangle 3, 4, and 5 applied to the frame. And we're looking for the moment of the force at point O. So before we write down the steps, let's do a simple analysis and write down the approaches that we're going to take for this problem. So first of all, if we take a look at this problem, everything is fit into the sheet of paper, or is a 2D problem. So I'm going to choose using the scalar formulation to calculate the moment about point O. And especially if you have a geometry given like that, you have an L-shaped beam, and we have 5 meters here and 2 meters there. Well, in order to find the moment arm of this force directly, it's not that easy to find moment arm perpendicular distance from the point O to the line of action. But if we can resolve the force into X and Y component, you'll see later it will be much easier to find the moment arm of the components. So the steps or the approaches that we're going to take will be first to resolve this 100 Newton force along the X and Y axis, and then determine the moment M of O using the scalar analysis for the two force components, and then use the principle of the moments to add those two components or two moments together. So we are given this figure with an L-shaped beam and with a force applied to it, and we're looking for the moment about point O. So the first step is to resolve the force into X and Y component. So remember, to resolve a force, you can resolve it at any point on the line of action. So usually it's easier if you resolve the force at a point that's on the structure, then it's easier for us to find the moment arm. So where to resolve the force is based on experience. So if after you're working with a lot of problems, you will know the best way to resolve a force. So if we resolve the force 100 at this point, now it's easier if you extend the line of action of the force a little bit, and also build the XY axis at this point that you're going to resolve. And then we're going to resolve the force into the X direction. So this is the f of X. And this f of X, which is parallel to this line with the number 4. Therefore, the magnitude of this will be 100 times 4 over 5. This is how we use this direction a slope triangle. Similar idea, we're going to resolve the force into the y-axis, and this will be the f of y, and it's parallel to the side with dimension 3. So the magnitude will be 3 over 5 times 100 and pointing downwards. So we can write down the result. At the same time, you can indicate the direction of both forces. Fx is pointing to the right, which is the positive x direction, and Fy pointing down, which is the negative y direction. But here, since we're using the scalar formulation, we are using the magnitude of the force and the magnitude of the moment arm, so not including the direction in your formula. So the second step is to find the moment of f of x and f of y respectively. So to find the moment, first we need to find the moment arm of each force. So let's start from the moment f of x, or the moment arm of f of x. So the moment arm is the perpendicular distance from the point O to the line of action. So we need to extend this line x-axis, and this fx is in the same direction or along the same direction as the x-axis. So here we're going to draw the perpendicular line from the point O to the line of action, and this is the d of x, which is 2 meter. Therefore, we can write the moment caused by force F of x about 0.0 MO Fx. So it will be the magnitude of the force times the moment arm d. So we have 100 times 4/5 times the moment arm. Let's write down the unit. So this is Newton and times 2 meter. And our result will be 160 Newton meter. And we need to indicate the direction of this moment, counterclockwise rotation or clockwise rotation, since that's important for using the scalar formulation. So based on the right-hand rule, this f of x will cause clockwise rotation. So we'll put clockwise rotation here by the answer. And same for the force Fy, and Fy force is in the direction of y-axis. So the moment arm from point O to the y-axis is along the x-axis, and the distance is 5 meters. So this is the d of y, which equals to 5. So same idea, we're going to calculate the moment of Fy about point O. And this time the F equal to 100 times 3/5 Newton, and the moment arm is 5 meter. So you have 60 times 5, which will be 300 Newton meter. And again, check with the right hand rule, the orientation or the rotation direction caused by F2 is also clockwise. So the last step, we're going to add them together, find the resultant moment. Since both moments will cause clockwise rotation, so their overall effect will be adding together. So we're going to add those two moments together, since they will cause, both of them will cause clockwise rotation. So together, they will cause a stronger rotational effect, which will be 160 plus 300 is 460 Newton meter, and indicate the direction, which is clockwise rotation. Example 2. Determine the moment about point B of each of the three forces acting on the beam. Point B locates over here, and we have three forces. We're not going to look for the overall resultant moment about point B, but each of the three forces. For each of the three forces, we need to determine the moment about point B. So since this is still a 2D problem, so let's use the scalar formulation to find the moment about point B again. So to use the scalar formulation, usually the first step is to resolve the force into the x and y components. And then we're going to determine the moment about B for the two force components for each force. Then add those two moments together to find the MB resulted from each force. So we're going to find the moment of each force about point B. So the solution, first let's resolve the force into their xy components. So F1 only has y component, so there's no need to resolve F1. For F2, we're going to resolve it again on this structure or on the beam right here, at the intersection between this F2 and the beam AB. So we can again make this force longer if that's easier for you to resolve the force. Resolve it into a vertical component and horizontal component. So this is f2 of x, and here's f2 of y. Again, to remind yourself which direction is x, which direction is y, you can draw this xy coordinate. Horizontal direction is x, and the vertical direction is y. And then use this direction triangle, or slope triangle rather, we can write down the magnitude of each component. So f2x is 3, so that's the line that parallel or in the x direction. 3 over 5 times 500. So we will do the calculation, which is 300 pound force, and f2y will be 4 over 5 times 500, which will be 400 pound force. Again, here we only need the magnitude, and direction will be indicated in your diagram or in your sketch over here. And same idea, we're going to resolve f3. And to resolve f3, just draw a perpendicular line to the x-axis. And again, to help you resolve that, you can build the xy coordinate at the point where you are going to resolve the force. So you will have f3 of y pointing down here, and f3 of x. And then we can write down the magnitudes of each force. f3x will be f3 160 pound force times sine 30 degree, which will be 80 pound force. And f3y will give us 160 times cosine 30. It will give us 138.564 pound force. So step 2, I'm going to write it over here to find the moment of each force. So for F1, so there's one way to do the sign notation or the direction notation is we draw the direction indicating that's the positive moment direction. So the moment about B by force F1 equals to the magnitude of F1, which is 375 pound force times the moment arm. So from B to F1 force, the moment, if you can see it, the moment arm is along this direction from the point arrow here to point B. So the length will be 6 plus 5, which is 11 feet. And then we do the calculation. So the answer will be 4,125 pound foot. And sometimes you will be asked to express the moment in another unit, which is kilopound feet. So it will be 4.125 kilopound times foot, and will be counterclockwise rotation. Okay, so this is how we express the result. Since moment is a vector, so you want to indicate the magnitude of the moment and also the direction. So for 2D, the direction of moment is either clockwise or counterclockwise. And now take a look at force F2. So we have F2x and F2y. We will treat them separately. So for F2x, this line of action of F2x pass through point B. In other words, point B is on the line of action of this force. Therefore, the moment of this force F2x will be 0. So there's only one component left. We'll have moment about point B, which is the F2y. And the moment arm for F2y is this 5 feet. From the point where we resolved the force F2 to point B. And this is the perpendicular distance from the point B to the line of action of this force B. So same idea, we indicate the counterclockwise rotation will be a positive moment, and we said F2x will have a zero moment, so we'll only have F2y times the moment arm, which is 5 feet. So F2y already did the calculation. It has 400 pound force in times 5 feet, which will give us 2,000 pound-foot, or 2.00 kilo-pound-foot. And we check with the right-hand rule, this rotation will also be counterclockwise rotation. So it's a positive value over here. And this is the moment of the second force. For force F3, and now if you take a look at the force F3y, it's also passed through point B. Therefore, force F3y doesn't have any moment, or the moment about point B will be 0. So we only need to consider the F3y, and the perpendicular distance from F3y to the point B is given here, which is 0.5 feet. Okay, so indicate the direction of rotation counterclockwise as positive, and this is F3, and F3y will have a 0 moment about point B. So F3 of x now, the moment arm is 0.5 feet, and F3x we have 80 pound force times 0.5 feet, and the answer will be 40 pound-foot. And then we use the right hand rule to check the rotational effect, and we figure out this F3x will also cause a counterclockwise rotation. Therefore, it's also a positive moment. And this is the final answer for force F3. And this problem is done. So if we take a look at this solution, if we're going to use the scalar formulation, it's easier if we first resolve the force into x and y component. And in this case, some of the forces will just pass through the point, like force F2x and force F3y. Then if the force passes through a point, or if the point is on the line of action, then this moment of this force will be 0, which will simplify the solution of this problem. And then we find the moment of the components that does have moment about this point, and we need to determine or figure out the direction, rotational direction, clockwise or counterclockwise, and to decide whether we need to add the components together or subtract one from another. Example 3. In this example, we have two forces given in vector form, F1 and F2. We are looking for the resultant moment by the forces about point O. So based on the principle of moments, we can calculate the moment of F1 about point O, and then calculate the moment of F2 about point O separately, meaning we can do R cross F1 and plus R cross F2. But since both forces F1 and F2 are passing through the same point A, which we call those two forces concurrent, then we can find the resultant moment of F1 and F2 first. Then we find the position vector from the point O to any point on the line of action. In this case, we'll find the point A, and then just perform cross production once, which will be ROA cross F, to find the moment about point O. So this will be the approach we're going to solve this problem. Step 1, find resultant force F. F, we're going to just perform the vector addition, F equal to F1 plus F2. So we'll add the corresponding components. So I component or X component is negative 100 I hat plus 130 J hat plus 175 K hat, and in the unit of pound force. In step 2, find the position vector. And this position vector can be any vector or any position vector from the point O to the line, to any point on the line of action. So in this case, there's only one point available on the line of action when we add these two forces together. Oh, by the way, if you're going to draw the resultant force F, it will look like this. Draw a parallelogram, and then the body diagonal will be the force F here. Okay, so this force will also pass through the point A. Now back to the position vector from the point O to any point on the line of action. So this position vector will be ROA. So we're going to write position vector ROA in Cartesian form because we need to perform cross product later. So this ROA will be the coordinate of A, subtract the coordinate of O, which is 0, 0, 0. Or we can use the imaginary path method to find the this position vector. So the position vector actually defines the relative location of 2 points in space. So if we have this position vector, we can take an imaginary walk from the tail of the vector to the head of the vector, and only along the x, y, and z direction. So first we need to go along the x direction. So the distance we travel along the x direction will be the x component. So we'll have 4, positive 4 I hat as the x component. Then we need to change direction to travel in a direction that is parallel to the y axis, and this distance is parallel to this elbow on the top portion, so it will be 5, and is the positive y direction, so it will be 5 j hat. And finally we'll change direction, travel along the z axis or parallel to the z axis, and the distance we traveled is 3, and it's positive 3. So this is my position vector. And the last step will be find the moment by using cross products. So for 3D problems, it's usually easier to use cross product than scalar formulation. So we'll have moment about point O equals to, again, position vector comes first, ROA cross force vector. So you have already learned how to perform cross product from your Engineering 106. So here I will just leave you to reveal the cross product if you forgot how to do it. And after I did the cross product, this is the moment about point O caused by two forces F1 and F2. And using cross product, the moment is a vector, is written in vector form directly, and the unit is foot times pound force, or pound force foot.